Right now, as you listen to these words, you are perfectly still. Yet you are also hurtling through space at unfathomable speeds. The Earth spins at over 1,000 miles per hour. Our planet orbits the Sun at 67,000 miles per hour. And our entire solar system races around the Milky Way galaxy at 490,000 miles per hour. Even our galaxy drifts through the cosmos at 1.3 million miles per hour. Despite all this motion, you feel nothing. You remain perfectly still in your perception. This contradiction between cosmic motion and perceived stillness mirrors our quest tonight. We embark on a journey to find something that may not exist, the edge of everything, the border of reality itself. Throughout human history, we've been obsessed with edges and boundaries. Ancient mariners feared sailing off the edge of a flat Earth. Medieval maps marked unknown territories with "Here be dragons." Our minds instinctively seek borders and limits, but the universe defies our intuition at every turn. Tonight, we'll explore what happens when you attempt to reach the edge of existence. Is there a cosmic wall? A boundary between something and nothing? Does space simply end? This isn't mere philosophical musing. Modern physics and astronomy have revealed startling truths about our cosmos. Truths that challenge our most fundamental assumptions about reality. About what it means to exist within this vast expanse we call the universe. We'll journey from Earth to the farthest reaches of observable space. We'll witness galaxies so distant their light has traveled for over 13 billion years to reach us. We'll confront cosmic horizons where space itself stretches faster than light can travel. The question, what happens if you try to reach the edge of the universe, opens doorways to even deeper mysteries. Is our universe finite or infinite? Does it have a center? What lies beyond what we can see? These questions have tantalized humanity's greatest minds. From Einstein to Hawking, from ancient philosophers to modern cosmologists. Tonight, we honor that curiosity by following the evidence where it leads. Through mathematical models, observational data, and theoretical frameworks, we promise to guide you through complex concepts with clarity and wonder. We'll translate the language of physics into accessible metaphors. We'll pause to appreciate the beauty in these cosmic truths. And we'll acknowledge when science reaches its current limits. Our journey begins with a simple truth. The universe is not what it seems. Space is not empty. Time is not constant. And the cosmos may be far stranger than our human minds evolved to comprehend. Yet somehow, remarkably, we can still understand it. Throughout this documentary, we'll return to a central theme. How does our quest to find the edge of everything change how we see ourselves? What does it mean to exist in a potentially boundless cosmos? And why do we feel such a profound need to know? In the coming hours, we'll travel billions of light years from Earth. We'll witness the birth of space and time. We'll encounter mysterious forces that shape the very fabric of reality. And we'll contemplate what it all means for us here on our pale blue dot. The answers may not be what you expect. The universe has surprised us at every stage of discovery. But one thing is certain. By the end of our journey, you'll never look at the night sky the same way again. Our contract with you is this. We will follow the evidence. We will distinguish between what we know and what we merely suspect. We will embrace mystery where it exists. And we will find profound wonder in the cosmic story that unfolds before us. So settle in as we begin our journey to the edge of everything. A journey that spans billions of years and trillions of miles. A journey to discover what happens when you try to reach the edge of the universe. If such an edge even exists at all. Let the stars guide us forward. Let curiosity be our compass, and let wonder be our reward. As we seek the ultimate boundary, the place where something might become nothing, the edge of the universe itself. But first, we must understand what we mean by universe, and why finding its edge has captivated humanity throughout our existence. The answer touches something fundamental in our nature. Our need to map, to explore, to understand our place. Because ultimately, this is not just about distant galaxies and cosmic horizons. It's about us, about our human need to locate ourselves within the vastness, to find meaning in a cosmos of incomprehensible scale, to understand our cosmic address. Chapter 2. Premise and Human Meaning. Why does the edge of the universe matter to us? Why do we care about cosmic boundaries we'll never personally reach? The answer lies in our evolutionary history. Our ancestors needed to understand boundaries to survive. Our brains evolved to map territories, to know where the safe ground ended, to comprehend the limits of our world. This instinct served us well for millions of years, until we looked up and wondered about the stars. The question of cosmic edges touches something primal in us. If the universe has an edge, what lies beyond it? If it doesn't, how do we comprehend infinity? Either answer is equally unsettling and fascinating to our finite minds. Throughout history, cultures have created stories to address this discomfort. Ancient Norse mythology described a cosmic tree, Yggdrasil, encompassing all realms of existence. Ancient Hindus envisioned cycles of creation and destruction spanning trillions of years. These weren't merely stories. They were psychological frameworks, ways to place human experience within comprehensible boundaries, to find meaning in a reality that extends far beyond our direct perception. Today, science has replaced mythology as our primary tool for mapping cosmic boundaries, but our emotional need remains the same. We seek to know where we stand in relation to everything else, to understand our cosmic context. When we contemplate the edge of the universe, we're really asking, is there an outside? Is there something beyond everything we know exists? The question creates a peculiar kind of existential vertigo, a simultaneous feeling of insignificance and wonder. Yet strangely, many find comfort in cosmic vastness. In a boundless universe, our everyday troubles shrink to their proper proportion. The mortgage payment, the difficult conversation, the uncertain future all exist within a much grander context. There is peace in this perspective. It's not the hollow peace of nihilism that says nothing matters, but the profound peace of cosmic belonging, of knowing we are made from the same elements as distant stars, that we are the universe experiencing itself. The question of cosmic edges also reveals the remarkable nature of human consciousness. We are star stuff that has evolved to contemplate star stuff, matter that questions its own boundaries. The universe has grown complex enough to wonder about itself. This is not mere poetry, it's literal truth. The carbon in your cells, the iron in your blood, the calcium in your bones all were forged in stellar furnaces. We are, in the most physical sense, the universe made conscious. Our quest for the edge represents something uniquely human. We may be the only entities in the cosmos who ponder such questions, who send telescopes into space to peer at the cosmic dawn, who build mathematical models of reality's boundaries. When we ask about cosmic edges, we're exercising a capacity that may be exceedingly rare in the universe, the capacity to wonder, to seek understanding beyond immediate survival, to contemplate the nature of reality itself. This pursuit has practical implications. Technologies developed for cosmological research have transformed our daily lives. The same physics that describes cosmic expansion influences the GPS in your phone. The same mathematics that maps galaxies powers modern computing. But beyond practical benefits, this quest offers existential orientation. In a seemingly chaotic world, cosmology provides perspective. It reminds us that the universe operates according to discoverable principles, that beneath apparent randomness lies profound order. Consider this: every civilization has placed itself at the center of its cosmology. Earth was the center of the universe, then the Sun, then the Milky Way. Each discovery has pushed us further from the center, yet each has expanded our understanding. Our modern cosmological models suggest something even more humbling. Not only are we not at the center, there may be no center at all. The universe may be infinite, or it may curve in ways that defy our intuition. Yet, rather than diminishing us, this knowledge elevates human consciousness to something extraordinary. We are the cosmos' way of witnessing itself, of appreciating its own beauty and complexity, of asking questions about its nature and boundaries. The vastness doesn't render us meaningless, it makes consciousness all the more precious. In a universe of such immensity, the fact that we exist to contemplate it is nothing short of miraculous. Our capacity for wonder becomes a cosmic treasure. As we continue our journey toward the edge, remember this paradox. The farther outward we look, the more we learn about ourselves. The more we understand about cosmic boundaries, the better we comprehend our place within them. Chapter 3. Origins and Early Science. The quest to find the edge of the universe begins with our earliest ancestors. Standing under starlit skies, they wondered about the celestial dome above. Was it a physical boundary? What existed beyond those twinkling points of light? Nearly every ancient culture developed creation myths to explain cosmic boundaries. The Babylonians envisioned Earth as a flat disk surrounded by a vast cosmic ocean. The ancient Egyptians saw the sky as a goddess, not torching over the earth. These weren't merely stories. They were humanity's first cosmological models, attempts to define the structure and limits of the observable universe. To answer the fundamental question, where does everything end? The ancient Greeks made the first substantial progress toward a scientific understanding. Around 240 BCE, Eratosthenes calculated Earth's circumference with remarkable accuracy. He used the angle of shadows in different cities during the summer solstice. This was a pivotal moment in human history. By measuring Earth's curve, Eratosthenes proved our world was spherical. He demonstrated that boundaries could be measured through observation and mathematics, rather than through myth and speculation. The Greek philosopher Aristotle proposed a geocentric model of the cosmos. Earth sat motionless at the center, surrounded by concentric crystalline spheres carrying planets, the sun, and stars. The outermost sphere marked the edge of the known universe. This model persisted for nearly 2,000 years, until the 16th century, when Nicolaus Copernicus proposed a revolutionary idea. What if Earth wasn't at the center? What if our planet orbited the sun instead? Copernicus hesitated to publish his heliocentric theory. Fearing religious persecution, he withheld his work until the year of his death, 1543. His book, On the Revolutions of the Celestial Spheres, changed our cosmic perspective forever. Imagine the psychological impact. For millennia, humans believed they occupied the cosmic center. Now, suddenly, Earth was demoted to just another planet. Our cosmic boundary had shifted. Our place in the universe had changed. Galileo Galilei advanced this revolution with his telescope in 1609. He observed mountains on the moon, spots on the sun, and moons orbiting Jupiter. The heavens weren't perfect crystalline spheres after all. They were physical places like Earth. These observations demolished Aristotle's cosmic boundary. There was no edge where the perfect heavens began. Space continued onward, filled with worlds that resembled our own. The universe had expanded dramatically in human understanding. Isaac Newton provided the next breakthrough in 1687. His law of universal gravitation explained how celestial bodies move. The same force that drops an apple pulls at distant stars. The cosmos operated under unified principles. Newton's universe was infinite, without edge or boundary. Yet it was also static and eternal. Stars were fixed against an infinite backdrop of space. This model satisfied humanity's questions about cosmic edges for more than 2 centuries. But new questions emerged. If the universe were truly infinite and filled with stars, why wasn't the night sky blindingly bright? This Olbers paradox, named after the 19th century astronomer who formalized it, suggested something was missing from our understanding. The puzzle deepened in the late 1800s. Astronomers discovered nebulae fuzzy patches of light scattered across the night sky. Were these cosmic clouds within our galaxy, or distant island universes beyond its boundaries? This question sparked the great debate of 1920. Astronomers Harlow Shapley and Heber Curtis argued opposing views. Was the Milky Way the entire universe, or just one galaxy among many? The answer came from Edwin Hubble in 1924, using the powerful 100-inch telescope at Mount Wilson Observatory. He observed individual stars in the Andromeda Nebula. By measuring their brightness, he calculated its distance. Hubble's conclusion was staggering. Andromeda lay far beyond the boundaries of our Milky Way. It was a separate galaxy, an island universe of billions of stars. In an instant, the cosmos expanded beyond imagination. But Hubble wasn't finished revolutionizing our understanding. By 1929, he had measured the light from dozens of distant galaxies. He discovered something astonishing. Almost all galaxies were moving away from us. And the farther they were, the faster they receded. This was the first evidence of an expanding universe. Space itself was stretching like the surface of an inflating balloon. This discovery fundamentally changed our conception of cosmic boundaries. The universe had a history. It was evolving. If galaxies were moving apart, then rewinding time would bring them together. This insight led to the Big Bang Theory, the idea that the universe expanded from an incredibly hot, dense state, that space and time themselves had a beginning. Belgian priest and physicist Georges Lemaître first proposed this primeval atom theory in 1927. He suggested the universe originated from a cosmic egg that exploded at the moment of creation, a radical concept that initially faced skepticism. Even Einstein initially rejected the idea, having added a cosmological constant to his equations to maintain a static universe. Later, he called this his greatest blunder. As evidence mounted for an expanding cosmos, by the mid-20th century, the question of the universe's edge had transformed. If the universe began in a Big Bang and continues expanding, what does this mean for its boundaries? Does expansion create an edge, or does it simply stretch existing space? Chapter 4. First evidence and scale. To understand the edge of the universe, we must first grasp its scale. The numbers are so vast, they become almost meaningless. Yet these measurements form the foundation of our cosmic understanding. Let's build this framework step by step. Start with Earth, our cosmic home, a sphere roughly 8,000 miles in diameter. Light travels this distance in just 0.04 seconds. Yet this planet, massive from our perspective, is merely a speck in a much larger system. Our Sun, a medium-sized star, contains 99.86% of all mass in our solar system. You could fit 1.3 million Earths inside it. Light takes about 8 minutes to travel from the Sun to Earth, crossing 93 million miles of space. The entire solar system spans roughly 5.6 billion miles across. Yet this vast expanse is just our immediate neighborhood. The closest star system to us, Alpha Centauri, lies 4.37 light-years away. That's 25 trillion miles. Let that sink in. If the distance from Earth to the Sun were represented by 1 inch, Alpha Centauri would be 4.5 miles away. This emptiness between star systems reveals the first truth about cosmic scale. Space is mostly void. Our Milky Way galaxy contains between 100 to 400 billion stars, arranged in a spiral disk roughly 100,000 light-years across. Light takes 100 millennia to traverse this distance. If the galaxy were shrunk to the size of North America, our solar system would be smaller than a coffee cup. The Milky Way isn't alone. It belongs to the Local Group, a collection of over 54 galaxies, including Andromeda, which will collide with our galaxy in about 4.5 billion years. The Local Group spans roughly 10 million light-years. Zooming outward, the Local Group is part of the Virgo supercluster, a collection of galaxy groups and clusters spanning 110 million light-years. And in 2014, astronomers discovered we're part of an even larger structure. This structure, named Laniakea Hawaiian for immense heaven, spans 520 million light-years. It contains about 100,000 galaxies. Yet Laniakea is just one of millions of superclusters in the observable universe, each containing countless galaxies. These superclusters form a cosmic web. Galaxy clusters create filaments and walls around vast cosmic voids, regions of space nearly empty of matter. Some voids span hundreds of millions of light-years. The largest known structure is the Hercules Corona Borealis Great Wall, a supercluster complex stretching 10 billion light-years across. It's about 10% of the observable universe's diameter, a truly incomprehensible scale. But what exactly do we mean by observable universe? This brings us closer to understanding cosmic edges. The observable universe includes everything we can theoretically detect. All light that has had time to reach Earth since the Big Bang. This cosmic horizon sits approximately 46.5 billion light-years away in all directions, not 13.8 billion light-years as you might expect from the universe's age. The discrepancy exists because space itself has been expanding as light travels through it. Here's where our intuition begins to falter. This 46.5 billion light-year radius is not an edge of the universe. It's merely the limit of what we can observe from Earth, a boundary created by the finite speed of light and the age of the cosmos. Think of it like standing in fog. You can see a certain distance before visibility fades. Someone standing a mile away sees a different circle of visibility. Neither of you is seeing an actual edge, just the limit of your perception. This cosmic horizon presents a profound limit to direct observation. We will never see beyond it, because light from greater distances hasn't had time to reach us. And due to cosmic expansion, much of it never will. The earliest light we can detect comes from the cosmic microwave background radiation, released about 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons, forming neutral hydrogen. This radiation appears uniform in all directions, suggesting the early universe was remarkably homogeneous, with tiny temperature fluctuations just 1 part in 100,000. These minute variations seeded the cosmic structures we see today. The James Webb Space Telescope, launched in 2021, peers closer to the cosmic dawn than ever before, revealing galaxies that formed just a few 100 million years after the Big Bang. Each new discovery pushes our observational boundary further back in time. But no matter how powerful our telescopes become, certain regions of space remain forever hidden. Due to cosmic expansion, galaxies beyond a certain distance recede faster than light. Their light will never reach us, creating a fundamental limit to observation. This boundary is called the cosmic event horizon. Unlike the observable universe, which grows larger as time passes, the cosmic event horizon shrinks as expansion accelerates. Distant galaxies continually slip beyond our view. If this expansion continues accelerating, eventually all galaxies outside our local group will disappear from view. Future civilizations might look to the sky and see only a handful of nearby galaxies, the rest of the cosmos hidden behind the cosmic horizon. These horizons, observational and eventual, aren't physical edges. They're informational boundaries, limits to what we can know about the universe, yet they don't tell us whether the universe itself has an actual edge. Does space simply end somewhere? Does it curve back on itself like Earth's surface? Or does it extend infinitely? The answer relates to the universe's overall geometry, which we've measured with remarkable precision. By mapping minute temperature variations in the cosmic microwave background, astronomers have determined the universe's geometry is remarkably flat. Not in the two-dimensional sense, but in the sense that parallel lines remain parallel. In a flat universe that expands forever, space could be infinite. Without edge or boundary, every direction extending endlessly. An endless ocean of galaxies stretching beyond our cosmic horizon, beyond even our mathematical modeling. As we stand at the precipice of Act 2 in our cosmic journey, a profound question emerges. If the universe has no edge, what happens when you try to reach one? And if space itself is expanding, what exactly is it expanding into? Chapter 5: Contradictions and Anomalies. As we journey deeper into our quest to find the universe's edge, we encounter puzzling contradictions. The cosmos refuses to fit neatly into our models. Like a mystery with conflicting clues, the universe presents anomalies that challenge our understanding. Let's examine the first major contradiction. If the universe began with a Big Bang and has been expanding ever since, then what exactly is it expanding into? This question seems reasonable, yet cosmologists consider it fundamentally misguided. The expansion of the universe isn't about galaxies moving through pre-existing space. Rather, space itself is stretching, like dots on an inflating balloon growing farther apart. Without the balloon expanding into anything, the surface simply stretches. But this analogy has limitations. A balloon's surface is two-dimensional, expanding into a three-dimensional space. Our universe has at least 3 spatial dimensions. So what higher dimensional space could it be expanding into? Or is the question itself flawed? Modern cosmology suggests the latter. Space may not need an outside to expand into. It can simply become larger. This challenges our intuition about boundaries, but our minds evolve to navigate earthly landscapes, not cosmic geometry. Another contradiction emerges from cosmic inflation theory. This theory suggests the universe expanded exponentially in its first trillionth of a second, growing from subatomic size to cosmic scale almost instantaneously. This rapid expansion explains several cosmic puzzles. Why the universe appears flat. Why distant regions share the same temperature despite never having contacted each other. Why we don't observe magnetic monopoles. Inflation elegantly resolves these issues. Yet inflation creates its own contradictions. What caused this exponential expansion? What made it stop? And most puzzling, could inflation have created multiple universes? Separate cosmic bubbles beyond our observable horizon. Some theoretical physicists, including Andre Linde and Alan Guth, propose that inflation might be eternal. While it stopped in our observable universe, it continues elsewhere, creating an infinite multiverse of bubbles, each with potentially different physical laws. If true, our universe might have an edge after all. Not an edge of space, but a boundary between cosmic bubbles. Regions where the rules of physics themselves change, where even the number of dimensions might differ. This brings us to another contradiction: the cosmic microwave background radiation. This afterglow of the Big Bang appears remarkably uniform across the sky. It contains certain anomalies that puzzle astronomers. One such anomaly is the cold spot, a region spanning roughly 1.8 billion light-years where the temperature is slightly lower than surrounding areas. Its size and coolness are difficult to explain with standard cosmological models. Some theorists suggest it could be evidence of a collision with another universe bubble, like 2 soap bubbles touching, leaving a visible mark. Others propose more conventional explanations, like a massive supervoid of relatively empty space. Then there's the axis of evil, an apparent alignment of temperature patterns in the cosmic microwave background, suggesting a preferred direction in space. This contradicts the cosmological principle that the universe should look the same in all directions. Most cosmologists believe these anomalies will eventually receive conventional explanations, statistical flukes, or observational artifacts. Yet they remind us that our cosmic models remain works in progress, with many mysteries still to solve. Another profound contradiction involves the rate of cosmic expansion, known as the Hubble constant. We have 2 primary methods to measure this value, and they give different results, creating what astronomers call the Hubble tension. When measuring nearby galaxies directly, we get one value, When inferring the expansion rate from the early universe, we get another. The discrepancy is subtle but significant. About 10% difference, well beyond the margin of error. This tension might reveal new physics. Perhaps dark energy has changed over time, or additional particles affected the early universe, or our understanding of cosmic distances contains systematic errors. The resolution remains elusive. Speaking of dark energy, perhaps the greatest cosmic anomaly of all. This mysterious force accelerates the universe's expansion, pushing galaxies apart ever faster. Yet, we don't know what it is, only that it comprises about 68% of the cosmic energy budget. The discovery of dark energy in 1998 shocked the scientific community. Astronomers expected gravity to slow cosmic expansion over time. Instead, they found it accelerating. This discovery earned the 2011 Nobel Prize in Physics. Dark energy presents a profound contradiction. It acts like anti-gravity on cosmic scales. It doesn't fit neatly into our understanding of fundamental forces. It could be an intrinsic property of space itself, or something more exotic. Some theoretical models suggest dark energy strength might increase over time, eventually tearing apart galaxies, stars, planets, and even atoms. In a scenario called the Big Rip, though current measurements indicate this outcome is unlikely. If dark energy represents the cosmological constant Einstein proposed, then its value is inexplicably tiny compared to quantum physics predictions. This cosmological constant problem creates a contradiction spanning 120 orders of magnitude, perhaps the largest discrepancy in all of science. Let's pause to appreciate what these anomalies reveal. Science progresses through contradictions, through observations that don't fit our models. Each anomaly isn't a failure, but an opportunity, a doorway to deeper understanding. Another cosmic mystery involves antimatter. For every particle, a corresponding antiparticle should exist. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated completely, leaving nothing but radiation. Yet here we are, in a universe dominated by matter. Some asymmetry in the early universe must have favored matter over antimatter, but we haven't identified the exact mechanism. Another clue that our cosmic story remains incomplete. The contradiction deepens when we consider black holes. These cosmic sinkholes warp space-time so severely that nothing, not even light, escapes their event horizons. They represent nature's ultimate boundaries, places where our physics breaks down. At a black hole's center lies a singularity, a point of infinite density, where space-time curves infinitely. Yet infinity rarely appears in physical reality, suggesting our theories remain incomplete. That quantum gravity might resolve these contradictions. Black holes present their own edge-related paradoxes. Information that falls into a black hole seemingly disappears. Yet quantum physics forbids information destruction. This black hole information paradox remains one of physics' great unsolved problems. These cosmic contradictions paint a humbling picture. Our understanding of the universe has advanced tremendously, yet fundamental mysteries remain. The cosmos continually surprises us, refusing to conform entirely to our mathematical models. As we seek the edge of the universe, these anomalies remind us to proceed with humility, to hold our theories lightly, to remain open to paradigm-shifting discoveries. For in cosmology, today's contradiction often becomes tomorrow's breakthrough. Chapter 6. Myths, misreads, and edge cases throughout our cosmic journey. We followed evidence and observation. But popular culture and internet discussions often present misconceptions about the universe's edge. Let's gently explore these myths, separating cosmic fact from fiction. Perhaps the most common misconception is that the Big Bang was an explosion in pre-existing space, that the universe expanded outward from a central point, like shrapnel from a detonation. This mental image, while intuitive, fundamentally misrepresents cosmic origins. The Big Bang wasn't an explosion into anything. It was the beginning of space and time themselves. Every point in today's universe was present at the Big Bang. There is no center from which everything expanded. Every galaxy sees others moving away. Imagine dots on a deflated balloon. As you inflate it, each dot moves away from every other dot. No dot sits at the center of expansion. Each legitimately sees others moving away from it. The universe operates similarly, but in 3 dimensions. Another common myth involves the observable universe. Many believe the edge we observe represents the actual boundary of existence. But our observable limit is merely an informational horizon, a boundary of what we can see, not what exists. Think of standing in the middle of the ocean. You can see about 3 miles to the horizon. Beyond that, the ocean continues. You simply can't see it from your position. Our cosmic horizon works similarly, but on an incomprehensible scale. A particularly persistent misconception is that astronomers have photographed the edge of the universe. Images from deep field observations are often misinterpreted this way, showing what appears to be a boundary beyond which nothing exists. In reality, these images simply show the limits of our telescopes. Beyond the faintest galaxies we can detect, space continues, with galaxies too distant or faint to observe. The apparent edge is an observational limit, not a physical boundary. Social media often circulates dramatic images claiming to show the end of the universe. These are typically artistic renderings, computer simulations, or misattributed astronomical images. Real cosmic photographs rarely look as dramatic or definitive. Remember that genuine astronomical images typically show tiny sections of sky. The famous Hubble Ultra Deep Field captured an area smaller than a grain of sand held at arm's length. A minuscule window into the cosmos, not its entirety. Another myth suggests scientists have detected an actual wall at the universe's edge. This misinterprets discoveries of large-scale structures like the Hercules Corona Borealis Great Wall. These aren't boundaries of space, just massive galaxy superclusters within the observable universe. Some internet sources claim NASA has encountered a firmament or solid boundary in space. This thoroughly modern myth often appropriates ancient cosmological models. No space agency has discovered any kind of universal boundary. No spacecraft has hit a cosmic wall. Let's address another common misconception: that beyond the universe lies nothing. This presupposes the universe has an outside. But if the universe encompasses all of existence, space, time, matter, and energy, then outside may be a meaningless concept. We struggle with this idea because our minds evolved to navigate bounded spaces. Rooms have walls, oceans have shores, lands have horizons. But the universe may not conform to these familiar patterns. It may have no exterior. Even language fails us here. Terms like beyond, outside, and edge imply boundaries. But if space itself is what expands, then these concepts may not apply cosmologically. Our linguistic limitations constrain our conceptual possibilities. Some spiritual traditions describe our universe as one bubble in a vast cosmic ocean. Modern physics offers a parallel in the multiverse hypothesis, yet crucial differences exist. Scientific multiverse proposals emerge from mathematics and observation, not from philosophical preference. The multiverse isn't a fringe concept. It emerges naturally from inflation theory, from string theory's mathematical landscape, from quantum mechanics' many worlds interpretation. Each approach suggests our universe may be one of many. But unlike mythological cosmologies, scientific multiverse models make testable predictions about cosmic microwave background patterns, about gravitational waves from bubble collisions, about fundamental constants and particle properties. They remain scientific hypotheses, not proven facts. Another misunderstanding involves the universe's shape. Many assume it must be spherical with an outer boundary, but cosmic geometry operates differently. The universe could be flat and infinite, or curved like a four-dimensional hypersphere, without any edge at all. Consider Earth's surface, a two-dimensional space without edges. You can travel indefinitely without encountering a boundary. The universe might have similar topology in higher dimensions. Finite, yet boundless. This leads to another misconception, that an infinite universe means anything possible must happen somewhere. This confuses infinity with probability. An infinite sequence of numbers doesn't guarantee every possible number appears. Similarly, an infinite universe doesn't guarantee every conceivable scenario occurs. Some claim we can see back to the beginning of time with powerful telescopes. This oversimplifies cosmic observation. We can observe light from approximately 380,000 years after the Big Bang, when the universe became transparent. Earlier eras remain directly unobservable. The James Webb Space Telescope has captured galaxies from very early cosmic history, but even it cannot see the universe's first few 100 million years. The era cosmologists call the cosmic dark ages, when the first stars and galaxies were just forming. Let's dispel another common myth, that the universe's expansion will eventually reverse, leading to a big crunch. Current observations strongly suggest otherwise. Dark energy's influence appears to ensure eternal expansion. The universe will likely expand forever, never contracting. Some speculate that the universe must have an edge because infinity cannot exist physically. But mathematical infinity and physical infinitude are distinct concepts. Modern cosmology accommodates both finite and infinite spatial models. The question remains open empirically. A subtler misconception involves the universe's age. The Big Bang occurred 13.8 billion years ago. Yet the observable universe spans 93 billion light-years across. How can this be? The answer lies in cosmic expansion during light's journey. When we observe distant galaxies, we see them as they were billions of years ago. But these galaxies have continued moving since emitting that light, and space itself has expanded. So their current positions extend far beyond 13.8 billion light-years from us. Another myth suggests black holes might lead to the edge of the universe, or to other universes entirely. While black holes dramatically warp space-time, no observational evidence suggests they connect to cosmic boundaries or alternate realities. Theoretical physics does explore concepts like wormholes, hypothetical tunnels through space-time, but these remain mathematical possibilities rather than observed phenomena, and would likely require exotic, possibly non-existent forms of matter to remain stable. As we address these misconceptions, we're not dismissing wonder or imagination. Rather, we're acknowledging that the actual universe, with its quantum fluctuations, expanding space, and relativistic time, is stranger and more fascinating than fiction. The myths we've explored reveal our deep psychological need for boundaries, for containment. For cosmic geography, we can mentally navigate. But the universe isn't obligated to satisfy our cognitive preferences. It simply is what it is. Chapter 7. Stakes and what changes if true. Why does it matter whether the universe has an edge? How would finding or not finding a cosmic boundary change our understanding? The stakes extend beyond abstract theory. They touch fundamental questions about reality, measurement, and humanity's future. Let's begin with practical considerations. Understanding cosmic geometry affects how we navigate and measure space, just as early seafarers had to grasp Earth's spherical nature. Future interstellar civilizations will need accurate cosmic cartography. If the universe is finite with an edge, we could theoretically map its entirety, given sufficient time and technology. But if it's infinite, complete mapping becomes impossible. No matter how advanced our civilization might become, some regions would forever remain unexplored. The question affects our telescopes and observational strategies. If space curves back on itself, like a higher dimensional sphere, we might eventually observe the same distant galaxies from opposite directions, creating a cosmic hall of mirrors. current measurements suggest space is remarkably flat, with a curvature radius at least 500 times larger than our observable universe. If there is cosmic curvature, it's so slight we cannot yet detect it, requiring even more precise future measurements. The universe's geometry also impacts light's journey through cosmos. In a closed universe with positive curvature, light rays eventually reconverge. In an open universe with negative curvature, they diverge faster than in flat space. These differences affect how we interpret distant observations. Consider gravitational wave astronomy. These ripples in space-time travel differently through variously curved geometries. As our detectors grow more sensitive, the pattern of gravitational waves might reveal cosmic topology, giving indirect evidence about universal boundaries. If the universe truly has an edge, what might we find there? Would physical laws change? Would space itself somehow terminate? Or would we discover a boundary between cosmic bubbles? Each possibility fundamentally alters our cosmological models. The stakes extend to fundamental physics. If our universe is one bubble in a multiverse, different regions might have different physical constants, explaining why our universe seems fine-tuned for complexity, without requiring a designing intelligence. This addresses the anthropic principle, the observation that physical constants seem precisely calibrated for life. If countless universe bubbles exist with varying physical laws, we naturally find ourselves in one compatible with our existence, like fish who only experience water. The question of edges relates directly to cosmic destiny. In a finite universe, all matter might eventually collapse back together. Or in an infinite expanse with accelerating expansion, matter might disperse until each particle loses contact with all others. Current evidence strongly favors the latter scenario, an eternal expansion driven by dark energy, leading to a big freeze or heat death, where entropy maximizes and no structured complexity remains, trillions of years in the future. But if our understanding of dark energy is incomplete, if it changes over cosmic time, other fates become possible. From the aforementioned Big Rip tearing apart atomic structures, to a big bounce where expansion reverses, the universe's boundary question affects timescales as well. In some models, time itself might have a beginning but no end. In others, cyclical epochs might follow one another eternally, the universe repeatedly expanding and contracting, like cosmic breathing. For practical human concerns, these questions might seem remote, yet they touch our deepest existential wonderings about beginnings and endings, about limits and possibilities, about our place within everything that exists. If the universe is truly infinite, then exact copies of Earth and everyone on it, statistically, must exist. Given enough space, matter will eventually arrange itself in every possible configuration, including duplicates of our world. A dizzying implication of boundless space. But infinity brings conceptual problems. How do we scientifically test something without boundaries? Can we meaningfully speak of everything if that everything has no limits? These questions transcend physics, entering philosophy and mathematics. The edge question impacts our search for extraterrestrial intelligence. In a finite universe, the number of possible civilizations is limited. In an infinite one, intelligent life must have evolved countless times, with profound implications for our cosmic significance. The boundary question relates to information theory as well. The universe has no edge and continues infinitely. Does it contain infinite information? Or does information, like matter and energy, become subject to cosmic limits? Some physicists, including Jacob Bekenstein, propose that any finite region of space can contain only a finite amount of information, proportional to the region's surface area, not its volume. This holographic principle suggests profound limits to cosmic complexity. The stakes extend to artificial intelligence and computation. The ultimate limits of computation depend on the universe's structure. In a finite universe, computational resources are ultimately bounded. In an infinite one, theoretical computational potential becomes limitless. Seth Lloyd of MIT calculated that the observable universe could perform a maximum of 10,120 operations on 1,090 bits of information. A mind-boggling number, yet finite, placing fundamental limits on what can be computed within our cosmic horizon. But if space extends beyond our horizon, if the universe has no edge, then theoretical computational capacity might be unlimited. Though practical access to those resources would remain constrained by the speed of light, creating regional computational boundaries. The edge question touches theology and spirituality as well. Many religious traditions describe creation as bounded with divine reality existing beyond physical space. How might these perspectives integrate with a potentially boundless cosmos? Some theologians embrace cosmic vastness as revealing divine creativity. Others see no conflict between infinite space and transcendent reality, viewing them as different ontological categories. The conversation between science and spirituality continues evolving with our cosmic understanding. Perhaps most profoundly, the universe's boundary question impacts how we understand consciousness. If reality has no edge, if existence extends infinitely in space, time, or dimensional complexity, what does this mean for minds that evolved to navigate finite environments? Our brains developed to process information relevant to survival, to track limited numbers of objects, to navigate bounded territories, to conceptualize finite durations. Yet we somehow comprehend mathematics of infinity. We ponder boundless space. This capacity to transcend our evolutionary programming is remarkable. We developed in specific ecological niches, yet contemplate realities far beyond immediate experience. Our consciousness somehow bridges the finite and infinite, the bounded and boundless. As our journey approaches its final act, we face the ultimate question, not just whether the universe has an edge, but whether human consciousness can truly comprehend the answer, whether finite minds can grasp potentially infinite reality. The stakes of our cosmic boundary question ultimately return to meaning, to how we orient ourselves within existence, to how we navigate between the infinitesimal and infinite, between the fleeting present and the cosmic timescale. If the universe has an edge, what lies beyond it? If it doesn't, how do we conceptualize boundlessness? These questions await us in our final exploration as we approach the limits of knowledge itself and confront the ultimate cosmic horizon. Chapter 8. Strongest competing theories as we approach the culmination of our journey to the edge of the universe. Let's examine the most compelling theories about cosmic boundaries. Not just what might happen if you try to reach the edge, but whether such an edge exists at all. Three primary theories dominate modern cosmological thinking about universal boundaries, each supported by mathematical models and observational evidence, each with its own implications for cosmic structure, each offering a different answer to our central question. The first theory proposes that the universe is truly infinite, without boundary or edge, extending forever in all directions. This infinite model aligns with the simplest interpretation of Einstein's equations and with our observations of cosmic flatness. In an infinite universe, attempting to reach the edge becomes meaningless, like seeking the end of the number line. No matter how far you travel, space continues, without diminishing or changing, forever extending beyond your cosmic horizon. This model suggests the cosmos contains an infinite number of galaxies, infinite stars, infinite planets, perhaps even infinite copies of Earth and everyone on it. Given enough space, matter would eventually repeat every possible configuration. The infinite universe theory elegantly solves certain cosmological problems. It removes the need to explain what lies beyond space. It aligns with our measurements of cosmic flatness, and it preserves the cosmological principle that no location is special. But infinity brings conceptual difficulties. Can something physically infinite actually exist? Or does infinity remain a purely mathematical concept? How would we experimentally verify an infinite cosmos? These questions challenge both physics and philosophy. The second major theory proposes a finite yet boundless universe. Like Earth's surface, which has finite area but no edge, this closed universe would curve back upon itself in higher dimensions, creating finite volume without boundaries. Imagine traveling in a straight line through this universe. You would eventually return to your starting point, having circumnavigated the cosmos without ever encountering an edge or boundary. Similar to how ships circumnavigate Earth, this finite but boundless model suggests interesting possibilities. Light from distant galaxies might reach us from multiple directions, creating repeating patterns in the night sky. Though we haven't observed such patterns, suggesting if the universe does curve, its radius far exceeds our observable horizon. Current measurements place tight constraints on cosmic curvature. If the universe does curve back on itself, it does so on a scale at least 500 times larger than our observable universe, making any such curvature exceedingly difficult to detect. In this model, reaching the edge remains impossible. Not because space extends forever, but because no edge exists. The universe loops back on itself, like walking around Earth's circumference without ever finding where the planet ends. The third major theory introduces the multiverse concept, proposing our universe is one bubble in a vast cosmic foam, each bubble representing a separate universe, with potentially different physical laws emerging from quantum fluctuations in an eternally inflating background. This model suggests our universe does have a boundary, a border where our cosmic bubble meets others, but this boundary exists in higher dimensions, beyond the three-dimensional space we experience, making it fundamentally unreachable through conventional travel. The multiverse theory emerges naturally from inflation. If the process that caused our universe's exponential early expansion continues elsewhere, then bubble universes would continuously form, creating an ever-expanding cosmic archipelago. Evidence for the multiverse remains indirect. Certain anomalies in the cosmic microwave background might represent scars from collisions with other bubbles. Statistical patterns and fundamental constants might reflect a larger ensemble. But definitive proof remains elusive. In the multiverse model, reaching the edge becomes theoretically possible, but practically impossible. The boundary exists where cosmic bubbles meet, but crossing it would require transcending our universe's physical laws, perhaps through higher dimensional travel. Each theory makes different predictions about what happens if you try to reach the edge. In the infinite model, you travel forever without reaching any boundary. In the finite but boundless model, you eventually return to your starting point. And in the multiverse model, the boundary exists but remains forever beyond reach, at least through any means of travel constrained by our universe's physical laws. The edge becomes a horizon that recedes as you approach. So which theory is correct? Current evidence slightly favors a flat, possibly infinite universe. But the margins of error in our measurements still permit slight curvature. And the multiverse remains a theoretical possibility supported by inflation models. The James Webb Space Telescope and other advanced instruments continue gathering data, mapping cosmic structure, measuring background radiation. Each observation further constrains our models, but definitive answers remain elusive. This uncertainty isn't failure. It's the honest state of cosmic science. We've progressed from mythological cosmologies to evidence-based models, from Earth-centered universes to multiverse theories, each step bringing us closer to understanding. Perhaps the most profound revelation is that all three theories share something remarkable. None proposes a simplistic wall at the edge of space. None suggests a place where reality simply stops. The universe, whatever its structure, is not bounded like everyday objects. Instead, each theory offers a sophisticated understanding of cosmic boundaries, as horizons of observation, as curved geometries, as dimensional transitions. far more subtle and profound than the naive concept of an edge. The question, what happens if you try to reach the edge of the universe, ultimately transforms. From a question about destinations into one about the nature of space itself, about the relationship between mathematics and physical reality, about the limits of human comprehension. As we prepare for our final revelations, consider how far we've come. From wondering about cosmic edges to contemplating infinite spaces, curved geometries, and bubble multiverses, our journey mirrors humanity's intellectual evolution. From boundary seekers to space-time explorers. Chapter 9. New Science, Instruments, and Paradoxes. Our quest to understand cosmic boundaries continues to evolve. As new instruments peer deeper into space, as theoretical physics explores higher dimensions, as computational models simulate cosmic evolution with unprecedented precision, let's examine how emerging science transforms our understanding. The James Webb Space Telescope represents humanity's most powerful eye on the cosmos. Positioned 1 million miles from Earth, observing primarily in infrared wavelengths, capable of detecting light from the universe's earliest epochs. Just a few hundred million years after the Big Bang, Webb's infrared capabilities pierce cosmic dust clouds that block visible light, revealing star formation in unprecedented detail, capturing light from the universe's first galaxies. Light that began its journey over 13 billion years ago, when the universe was in its infancy. Early Webb observations have already challenged existing models, revealing massive galaxies formed earlier than expected, suggesting the early universe evolved faster than our simulations predicted, prompting revisions to cosmic formation theories. These discoveries don't directly reveal cosmic edges, but they refine our understanding of cosmic evolution, each observation providing another puzzle piece, helping us trace the universe's history backward toward its origins, and forward toward its ultimate fate. On Earth, enormous new telescopes prepare to join the search. The extremely large telescope in Chile, with its 39-meter primary mirror, the 30-meter telescope planned for Hawaii, the giant Magellan telescope in Chile, each designed to gather unprecedented amounts of light. These instruments will map cosmic structure with extraordinary precision, detecting faint galaxies at extreme distances, measuring slight gravitational lensing effects, potentially revealing subtle signs of cosmic curvature, evidence that might distinguish between competing boundary theories. Meanwhile, entirely different observatories monitor the cosmos through non-optical means. Gravitational wave detectors like LIGO and Virgo sense ripples in spacetime. Neutrino observatories capture ghost-like particles that pass through ordinary matter. Radio telescopes map hydrogen gas across cosmic distances. This multi-messenger astronomy creates a comprehensive cosmic portrait, each detection method revealing different aspects of the same phenomena. Like examining an object simultaneously through touch, sight, and sound, building a more complete understanding than any single method could provide. Gravitational waves offer particularly promising insights into cosmic boundaries. These ripples in space-time travel unimpeded since the earliest moments of the universe, potentially carrying information from before the cosmos became transparent to light, revealing conditions closer to the Big Bang than ever before. Future space-based gravitational wave observatories like LISA will detect much lower frequencies, potentially sensing primordial gravitational waves from cosmic inflation itself, waves that might carry imprints of quantum fluctuations from the universe's first instance, perhaps even evidence of other cosmic bubbles. Neutrino astronomy adds another dimension to our cosmic understanding. These nearly massless particles interact so weakly with matter that they pass through Earth unimpeded. They reach us from places optical light cannot escape, like the cores of supernovas or the vicinity of black holes. By combining these diverse observations, astronomers construct increasingly detailed cosmic maps, charting galactic superclusters, mapping voids between them, tracing the cosmic web of dark matter, all to determine whether space curves, extends infinitely, or harbors boundaries. Computational advances further enhance our cosmic understanding. Supercomputers now simulate cosmic evolution from the Big Bang to the present, modeling how quantum fluctuations grew into galaxies, how dark energy influences expansion, how structure forms across billions of years. These simulations help distinguish between competing theories by predicting observable consequences for each model, which we then compare with actual telescope observations. The agreement between simulation and observation is often remarkable, though discrepancies continue to drive scientific progress. As our instruments and models advance, new paradoxes emerge, each discovery answering some questions while raising others. This pattern of resolution, creating new mystery, characterizes the scientific journey, a path of ever-deepening understanding rather than final answers. One emerging paradox involves cosmic inflation itself. The theory elegantly explains the universe's flatness and homogeneity. Yet the mechanism that drove this exponential expansion remains mysterious, as does the transition from inflation to normal expansion. Another paradox involves quantum entanglement across cosmic distances. Quantum mechanics allows particles to maintain instantaneous connections regardless of separation. Yet, relativity forbids faster-than-light information transfer, suggesting deeper connections between quantum physics and space-time structure. Perhaps the most profound paradox involves the universe's habitability. The fundamental constants of physics, like the strength of gravity and electromagnetism, appear precisely calibrated for complexity. Slight changes would prevent atoms, stars, or life from forming. This fine-tuning creates an explanatory challenge. Is it remarkable cosmic coincidence, evidence of design, or the natural result of a multiverse where different bubbles have different physical laws? Each possibility carries profound implications for cosmic boundaries. The multiverse hypothesis addresses this fine-tuning paradox. If countless universe bubbles exist with varying physical laws, we naturally find ourselves in one compatible with our existence. A form of cosmic natural selection. Yet the multiverse theory creates its own paradoxes. If infinite universes exist with every possible configuration, then infinitely many identical copies of you exist, along with nearly identical versions, and versions where cosmic history differs in every conceivable way. Such implications strain our conceptual frameworks, challenging basic notions of probability and uniqueness, leading to philosophical puzzles about identity and possibility, about what it means for something to exist at all. These paradoxes aren't merely abstract curiosities. They guide research directions, inspire new experiments, motivate theoretical breakthroughs. The tension between competing explanations drives science forward, toward ever more comprehensive cosmic understanding. As we prepare for our final revelations, consider how these advancing frontiers transform our original question. What happens if you try to reach the edge of the universe? The question evolves from simplistic geography to profound exploration of reality's fundamental nature. Chapter 10. The Big Reveal. We've journeyed through cosmic history, explored competing theories, examined emerging science. Now we return to our central question. What happens if you try to reach the edge of the universe? The answer, revealed through our exploration, contains unexpected depth. First, we must acknowledge a fundamental truth. The universe doesn't conform to our intuitive expectations about edges and boundaries. Cosmic reality operates according to principles far removed from our everyday experience. Principles revealed through mathematics and observation rather than common sense. Our most comprehensive answer emerges from synthesizing everything we've explored, drawing on observational evidence, theoretical frameworks, and the fundamental laws of physics to reveal what would actually happen during a journey toward cosmic boundaries. Imagine embarking on this impossible journey. Traveling outward from Earth at nearly the speed of light, passing neighboring stars. Exiting the Milky Way, traversing intergalactic space. What would you encounter? For billions of light years, you'd pass galaxies similar to those in our vicinity. The universe appears remarkably homogeneous at large scales. Clusters and superclusters would come and go. The cosmic web would surround you, with no sign of any approaching edge. But something profound would happen during your journey, something that reveals the true nature of cosmic boundaries. The universe around you would appear to accelerate in its evolution, as the light reaching you comes from increasingly recent cosmic epochs. This occurs because you're moving toward regions whose light hasn't had time to reach Earth yet. Regions beyond our observable universe. You'd witness cosmic history unfolding differently than observers on Earth. Your observable universe would differ from ours. This reveals our first major insight. The observable universe is observer-dependent. Each point in space has its own cosmic horizon, its own sphere of visibility. What appears as an edge from one location is simply the limit of observation, not a physical boundary. As you continue outward, another phenomenon emerges. The galaxies ahead would appear to move away faster. Due to cosmic expansion, eventually, you'd reach regions where space expands faster than light travels, creating an apparent horizon you cannot cross. This expansion doesn't violate relativity. Space itself can expand at any rate. It's not matter moving through space, but space itself stretching, creating distances at rates exceeding light speed, an insurmountable horizon for any physical traveler. This reveals our second major insight. Cosmic expansion creates horizons that recede as you approach them. Like trying to reach the horizon at sea, the boundary moves as you move, making the edge fundamentally unreachable, no matter how fast or how long you travel. But what about the universe's overall structure? Is it infinite or finite? Does actual space have an edge? Current evidence suggests three possibilities, each with different implications for boundary seekers. If the universe is infinite and flat, as current measurements suggest, then space extends forever in all directions. No matter how far you travel, more galaxies await. More clusters, voids, and filaments. Endless cosmic structure without boundaries. In this scenario, the question of reaching an edge becomes meaningless. Like asking what's north of the North Pole, the concept of an edge of everything simply doesn't apply. Space continues without limit or boundary. If instead, the universe is finite but boundless, curved like a four-dimensional hypersphere, then traveling straight ahead eventually brings you back to your starting point, having circumnavigated the entire cosmos. Without ever encountering an edge, this curvature would be imperceptible locally. Just as Earth's surface appears flat to us despite its global curvature. Only by traveling enormous distance, far beyond our observable universe, would the cosmic curvature become apparent. And if the multiverse theory proves correct, our universe is one bubble among many, then boundaries might exist where cosmic bubbles meet. But these boundaries would exist in higher dimensions, beyond the three-dimensional space we experience. Crossing such boundaries would require transcending our universe's physical laws, perhaps through quantum tunneling or higher dimensional movement, beyond any technology we can currently imagine, and potentially beyond the realm of scientific testability. Having explored these possibilities, we can now answer our central question with clarity. What happens if you try to reach the edge of the universe? The answer contains three profound truths. First, you never reach a physical edge or boundary, regardless of which cosmological model proves correct. Either space extends infinitely, or curves back on itself, or transitions through higher dimensions. But nowhere does it simply end in the conventional sense. Second, you continually encounter new horizons, regions beyond which observation becomes impossible from your current position. As you move, these horizons move with you, revealing new cosmic vistas while maintaining the fundamental limits of observation. Third, your journey transforms your understanding of boundaries themselves. You realize cosmic edges aren't physical walls, but horizons of knowledge, not places where space ends, but limits to what can be observed from a given position. This answer may seem unsatisfying to minds accustomed to definitive edges, to clear boundaries between here and there, between something and nothing. But the universe isn't obligated to conform to our intuitions. It simply is what it is. The desire to reach the edge represents something profoundly human. Our need to map, to explore, to comprehend. To place ourselves within a navigable cosmic geography. To transform the infinite into the finite. The incomprehensible into the comprehensible. Yet the cosmos reveals a deeper truth, that boundaries themselves are largely constructs of perception. That the universe operates according to principles far more subtle, far more mathematical, far more beautiful than simplistic edges would allow. Perhaps the most profound revelation is this: we don't need to physically reach the edge to understand it. Through observation, mathematics, and theoretical physics, we've mapped cosmic structure, traced its evolution, projected its future, all while remaining on our pale blue dot. This represents humanity's greatest achievement, not conquering space through physical travel, but comprehending it through observation and thought, using telescopes as time machines, mathematics as conceptual spacecraft, theories as maps of the unmappable. So what happens if you try to reach the edge of the universe? You never arrive at a physical boundary, but you discover something far more profound, that the concept of edge itself transforms, from simplistic geography to profound epistemology, from places where things end to horizons of what can be known. As our cosmic journey concludes, we find ourselves in a beautiful paradox. We sought the edge of everything, yet discovered there may be no edge at all, or that the edge exists only in relation to the observer, a horizon of knowledge rather than a physical boundary. This paradox offers a profound form of comfort. The universe doesn't simply end. There is no cosmic cliff beyond which nothing exists, no wall separating being from non-being. Reality extends beyond our vision, beyond our measurement, perhaps beyond our comprehension. Yet within this vastness, we find meaning, not despite cosmic scale, but because of it. Our consciousness, this remarkable capacity to wonder, to question, to understand, may be vanishingly rare in the cosmos, making each moment of awareness precious beyond measure. We began by asking about the edge of the universe. We end by recognizing that boundaries exist primarily in our perception, that the cosmos invites perpetual exploration, endless questioning, infinite wonder. As we continue our journey through the stars, we invite you to join us for more cosmic explorations on Science Asleep.